So we're going to be discussing how we can take these functions and actually begin to put a graph together to see what's going on. I mean, if you think about it in the business world, it's not going to come to you in the form of a graph, but there's a lot of important information you can get from a graph. So if we can take that equation and figure out how to put it in graph form, that would be helpful. So let's review a few things that hopefully you remember from, say, algebra. If you're looking at a graph and your graph is moving, as you go from left to right, it's going up, what would you say your graph is doing? Increasing. If as I move from left to right, if I'm going up, that would be increasing. Now, if I'm moving from left to right and the graph is coming down, that would be decreasing, correct? Okay, now, here's the part that you would have been stuck on if you were trying to graph in college algebra. Whenever I teach the graphing section in college algebra, and we are looking at polynomial functions, something that's going to have higher an exponent than 2, if it's cubic or something to the 4th power. There's a lot of information that algebra will tell us about the graph. We can figure out what the ends are doing. We can figure out whether overall the function is increasing or decreasing. But what we have trouble with is if there is something like this going on, where you might call them hills and valleys within the curve. You're going to have places where it changes direction. Maybe it goes from increasing to decreasing, or it goes from decreasing to increasing. The problem is, in algebra, we had no way of finding exactly where those turning points occurred. So if you were in my college algebra class and I had asked you to give me a sketch of that polynomial function, you just had to kind of guess where you thought the turning points were. I didn't count off if you weren't exactly where they should be, because we discussed the fact without calculus, we don't have a way of finding where they occur. But now, because we're doing calculus, we're going to be able to figure out where they occur. And the way we do it is we're going to find what's called the critical values. Those critical values are going to be the x value where the derivative, f prime of x, equals 0. Now, tell me again, because I know it's been spring break since we last met, and it's easy to forget some stuff. When I take the derivative of a function, what's it actually letting me find? The derivative is a tool I use to find the, say it a little louder, Jordan. Slope. There you go. It lets me find the slope of the original function at any particular point on that function, because that's what it's finding, is the change in y over the change in x. Well, now think about it for a minute. If my slope is 0, what kind of line would that be? My tangent line would be horizontal, wouldn't it? And if that tangent line is horizontal, that's because that has to be a turning point there. It's either going from increasing to decreasing, or it's going from decreasing to increasing. So that's going to let me find where I have those turning points. I can also figure out if there's any value where the derivative doesn't exist. In other words, that would mean that instead of having a horizontal tangent line, it would be vertical. Now, we haven't really looked at many of those, but what I would tell you is sometimes you may see a graph that does something like this. And instead of having, say, a curve there, it has what we might call a cusp. Okay? It's almost like it comes to a sharp point and it backtracks a little bit, or it looks like it backtracks a little bit. And that would actually have a tangent line that does not exist, that would be undefined. So those are good, and that's only going to happen if I've got a rational function. I would have to have something with a denominator, and I would figure out when the denominator is 0. to potentially have a value there. So here's what we're going to be doing today. We're going to find the first derivative for our function, and we're going to use it to test for local extrema. Now, local simply means if we had a graph like this, then we would have a local maximum wherever that tangent line had a slope of 0, okay? But it's not what we would call an absolute maximum, because if it's an absolute maximum, it means there is no point that has a higher y value on the graph than this one. And if I look at what's going on the ends, that's not going to be true, right? Because this is going to continue upward a long way, actually heading toward infinity, if I'm looking at this part right here, okay? And I would also have a local minimum wherever this tangent line has a slope of 0 in this area where the x value exists, but that's only going to be a local minimum because this part of my graph is going to continue on toward negative infinity. Okay, so we can't have an absolute maximum, but that means that it's the, like, think about a parabola. If I were to picture a parabola, there's one turning point, isn't there? Sure, right here is where that turning point occurs. And in addition to being a local maximum, it would also be an absolute maximum because that's the absolute highest y value that we're going to get anywhere on this graph. Okay? So we're going to follow this test. Once we find our derivative and we set it equal to 0, and that gives us this value that we know is a critical value, we're going to run what's called a sign analysis. We're going to look to see on either side of that point what kind of numbers would, what kind of values would I get if I use x values that are to the left of this? Would they be positive or negative when I plug in? When I look to the right, I'm going to see if they would give me positive or negative. And a minimum occurs if everything to the left of my value gives me a negative, and then everything to the right of that value is positive. It's telling me I'm going from decreasing to increasing, and that would make it a local minimum. If, on the other hand, I go from positive to negative, then that would make it a local what? Oh, come on. From positive to negative. That'd be a local maximum, exactly. And if you need to, use the little hand signs to help you figure this out. It may be, though, that I test on either side of this number, and if there's no sign change, let's say it's negative on both sides, or it's positive on both sides, then that tells me it's not going to be a maximum or a minimum. Something else happens there, and I may need another test, which we'll talk about on Wednesday, to help me figure out what it is. So let's look at this. The very first thing we're going to do is just practice to make sure we have not forgotten how to find derivatives. So can you tell me, if this is my function, x cubed minus 27x plus 12, what would be my first derivative? 3x squared minus 27. And am I done? Absolutely. If you remember, when I have multiple terms, I can take the derivative of each term separately. And so using that power rule, that's how we got 3x squared. Then we have the minus 27, and anytime I take the derivative of a constant, it is 0. Now, let's turn the page. And what we're supposed to do is find the critical values of this function. So I'm going to take the 3x squared minus 27, and to find critical values, I set this equal to what? Yeah, I want to know when the derivative would be equal to 0. Okay, talk to me about how I'm going to solve this now. What would you do? What should I try to do on the left side? Well, I could add 27, but I'm going to make a suggestion. Is it possible to factor? Because I have a common factor here, don't I? What is it?
3.
So if I factor out a 3, what will I have in parentheses? X squared minus 9. Very good. And can I factor x squared minus 9? Yes, it's a difference of squares, isn't it? How does it factor? Okay, we got to make sure we don't forget how to factor. When I say it's a difference of squares, it's because my first term is a perfect square, my last term is a perfect square, the sign in the middle is subtraction, so it factors into 2 parentheses. What will they be? There you go. X plus 3 times x minus 3. The order I write those in does not matter. But I take the square root of x squared, goes in the front of each parenthesis, square root of 9 goes at the end. One parenthesis gets a plus, one gets a minus. Now, in order to solve this, I set each factor equal to 0. Now, I actually have 3 factors here, correct? 3 times the x plus 3 in the first parentheses times the x minus 3 in the second parentheses. But my common factor was just 3. It didn't have a variable with it. So if I set 3 equal to 0, that doesn't even make sense, does it? Nothing to solve there. So I'm going to set x plus 3 equal to 0 and x minus 3 equals 0. And what are my 2 critical values?
Positive and negative.
Correct. Either a positive 3 or a negative 3. So I'm going to have a negative 3 and a positive 3 that we're going to call partition numbers, okay, or these critical values. And I'm going to show you in a second, when we get to this point, how we're going to use these to help us figure out if we have a local maximum or a local minimum that may be occurring at these 2 points. But here's what I know right now. If I have a local max or a local min, it could only occur either at negative 3 or positive 3. Those are the only possible places one could exist. And I wouldn't have known that in algebra. I need the calculus to help me find it. Now, if you look at number 2, what do you notice is different about this function? It's a fraction. It's a rational function, which means that we have a denominator that has a variable in it. Okay, so if I need to find the derivative, because that's what I'm going to have to use to figure out if I have any critical numbers, how will I find the derivative of this thing? What do I have to use to get it? I think I would use the quotient rule. Now, I could rewrite it and potentially use the product rule, but if I do that, I'm going to have to use the chain rule within the product rule. So we might as well just try using the quotient rule. Okay? Let's see if you remember what the quotient rule is. How do we use it? I'll get you started. It's low what? D high. And what is the derivative of this numerator? What's the derivative of 19? 0, right? Then what? Minus, what comes next? High, D low. All right, what's the derivative of that denominator? Just 2. Over, what? Low squared. So I have 2x plus 6 in parentheses squared. Now, cleaning this thing up, my numerator actually cleans up to be something pretty simple, because if I multiply 2x plus 6 times 0, that becomes what? 0. And I have 0 minus 19 times 2, which is, what's a negative 19 times 2? Negative 38. Over, and just leave this in factored form. 2x plus 6 in parentheses squared. You don't have to expand it out. So that's going to be my derivative. Now, in order to find the critical values, what would I do? I would set this function equal to 0. Now, the problem I've got is, can this function equal 0? What's the only way a fraction could ever equal 0? If 0 shows up where in the fraction? In the numerator. What's in my numerator? Negative 38. No variable with it. Is there any way that numerator can ever become 0? So here's what that means. This thing will never equal 0. Correct? Okay. Now, can the denominator equal 0? The denominator could equal 0 if x is what? Say it again. Correct. If I divide both sides by 2 here, I'm going to get x equals negative 3. But there's a little bit of a problem with using that, because if I go back and I look at the original function, is it part of my domain, or was it already excluded in my domain? Think about it. If I try using negative 3, would that exist in the original equation? No. So since this is undefined in the original equation, what that tells me is there are no critical values. Okay? No critical values, because there is no value that I can get if I set the derivative equal to 0 that would make the derivative 0. That doesn't exist. And the only value where the derivative is undefined is also undefined in the original function, which means it's not part of my domain. There's going to be a vertical asymptote that occurs there. So negative 3 doesn't exist. And that would mean that I'm not going to have a max or a min. Does that make sense? Okay, so those are 2 examples of what happens, or what can happen, when you are looking for those critical values. You won't always have one, but you can't have a max or min unless you do have a critical value. Okay, let's go to the next page. And now with this function, and notice, if I were to ask you before we even start, can you tell me what kind of a graph this is going to be? It's a parabola. We know that because this is a quadratic equation. We're going to start with something that's really basic and simple, because we already know quite a bit, hopefully, about quadratic equations. And I want to show you, when you are looking for these maximum and minimum values, how you're going to put all these pieces together. So the first thing we'd have to do is find any possible critical values. Then we're going to check to see if they could be a local max or a local min. And the way we do that is with this sign analysis. And we'll be able to tell if the numbers to the left of this number, this critical value that we come up with, are they increasing or are they decreasing? Okay? And then we could actually identify the intervals where the function is increasing or decreasing based on what we get from this sign analysis. And then we'll know if we've got a maximum or a minimum that occurs. And from there, we'll be able to put all the pieces together and sketch our graph. So here's what we're going to start with. In order to get any information from this, as far as increasing, decreasing, do I have a maximum, do I have a minimum, what am I going to have to do first with this function? Find the derivative. There you go. So f prime of x will equal, what's going to be the derivative? 2x squared. When I differentiate it, I get 4x. Good. And then I have that plus 0 on the end, which I do not need. Now that I have the derivative, I need to do what with it? Set it equal to 0. So if 0 is equal to 4x minus 16, can you tell me what's going to be my critical value? It's going to occur when x equals 4. I would add 16 to each side, and then if I divide each side by 4, that's how I come up with x equals 4. Okay? So here's what we're going to do with it. We're going to draw a little number line. What I'm interested in is what happens on either side of 4. I know at x equals 4, the slope is 0. The derivative will give me the ability to determine the slope on either side. So what I want to figure out is if the slopes are positive to the left of this, that means that they're increasing. If the slopes are negative to the left of this, it would tell me that my graph is decreasing. So I need to look at this derivative, the 4x equals 16, and let's pick some number to the left of 4 to use as a test point. So think of some number that's smaller than 4. 0 is probably the easiest number to plug in. So I'm going to plug in 0 and see what happens. If I plug in 0 to the derivative, I get 4 times 0 minus 16. I really don't care what the number is. I just need to know if it's a positive number or a negative number. What is that going to be? That's negative. Okay? Because 0 minus 16 tells me I've got a negative number. Now, pick some number to the right of 4, and let's use it as a test point. 5, that would work. So let's find out what f prime of 5 is. If I have 4 times 5 minus 16, again, I really don't care what the number is. I just need to know the sign. Is that going to be a positive number or a negative number? Positive. 4 times 5 is 20. 20 is bigger than 16. So when I subtract, I'm going to get a positive number back. Now, let's see if you can tell me what do I have going on at 4 on this original function. Is it a local max or a local min? I heard somebody say min. And how do you know that? Because it goes from decreasing to increasing. And you can use your hand motions to help you figure that out if you want. That means that is a local minimum. Because this thing is going down. Once it gets to 4, it flattens out and then it comes back up. Okay? So here's what they want us to answer. Now that we have found this information on A, you're supposed to give me the interval where the function is increasing. Now, because this is a parabola, all right, I already know it's got to be a U shape. So it's either going to be opening up or it's going to be opening down. Since this is a local minimum, and if we actually think about what we should already know about quadratic equations, the fact that there's a positive value in front of the x squared should have told me this is a parabola that opens up, right? So tell me the interval where this parabola would be increasing. It starts increasing at what value? Exactly. When it gets to 4, it's technically that turning point. So from 4 to where is this function increasing? There you go. So in interval notation, that's how you answer the question, where is it increasing? From 4 to positive infinity. Now, how would we identify the interval that's decreasing? Now be careful. Remember, when we give our interval, we've always got to go from least to greatest. So we don't start at 4. We have to start where? There you go. From negative infinity to positive 4 is where the interval is decreasing. So far, are we okay? All right. Here's what C asks us to identify. The local extrema. Now, extrema simply means it's a maximum or a minimum. Local is, if I find one here, I know for sure it's local. What's going to tell me if it's a maximum, an absolute maximum or an absolute minimum is what's happening on the ends of this graph. Okay? Since this is a parabola and we know it's doing this, it opens up, is this also going to be an absolute minimum? It is, because there will not be any y value that gets any smaller than the y value we get when x is 4. So if it asks you to identify those extrema, we're going to have to take the x value where we know the minimum occurs And how do we get the y value that goes with it? What would we have to plug that into? Would I plug it into the derivative, or would I plug it into the original? The original. Excellent. I need to take 4 and plug it into the original function in order to know where is the point where that extrema occurs. So I'll have 2 times 4 is going to get squared minus 16 times 4 plus 33. Okay, you guys clean that up and see if you can tell me where does this local minimum occur. Have you got it? Where is our local and our absolute minimum? What's the ordered pair? 4, comma 1. Correct? Think order of operations. If you had any trouble cleaning this up, remember you got to square the 4 first. So 4 times 4 is 16. 16 times 2 was 32. Then you had to subtract 64 and then add 33 to it. And that's how you get a positive 1. Okay, so far are we all right? All right. Now I have x cubed minus 27x plus 12. And we're going to do the same thing that we just did. We want to be able to give where is it increasing, where is it decreasing, and then do we have any extrema? And are they going to be local or are they going to be absolute? And I'm going to go ahead and tell you a little bit about how you tell that. We're good with, as long as it's quadratic, right? If it's a parabola, you can tell that either it's going to open up or it's going to open down. And what tells us whether it opens up or opens down? We look at which part? We look at the sign in front of the x squared, right? If it's positive, it tells us the parabola opens up. If it's a negative number in front of the x squared, it tells us it opens down. Now, if you get an exponent that's higher than 2 on your lead term, this one is cubic, you need to know a little bit more about how to figure out if it's going to be, what's going to happen on the ends of your graph, because that's going to tell us whether we've got absolute maximums or minimums. So let me give you this information. If you didn't do this in college algebra or it's been a while, let me remind you. If you look at the first term, we need to pay attention to both parts, the coefficient and the exponent. So if the exponent is odd, then it means that our ends are doing different things, okay? Either one goes up and one goes down, or it's the reverse direction. The first side goes up and the other side goes down, okay? As long as the exponent is even, then they do the same thing, either both up or both down, all right? If they're odd, they do different things. If they're even, they're going to do the same thing on the ends. The coefficient will tell us which direction they're going to go. So as long as it's even, it's just like a parabola. As long as it's positive, then it's going to be up, up. If it is a negative coefficient and the exponent is even, then it's going to be down, down. Okay? They're both going to do the same thing. In this case, because our coefficient is positive and odd, think about it in terms of slope, okay? If it's odd, that means they're doing different things. So if I just pay attention to the ends, as long as it's positive, then that means it's going to be down on the left, up on the right. That's what this thing is going to do, okay? If it happened to be negative and odd, then it would be up on the left and down on the right. It would be decreasing. All right? So if it's positive coefficient, odd exponent, then it looks like this first one, which is down on the left, up on the right. If, on the other hand, it's a negative coefficient with an odd exponent, then it's up on the left and down on the right. Okay? And as long as the exponent is even, it does the same thing you would expect a parabola to do. Okay, so here's what that tells me. Before I even start, do I have any absolute maximums or minimums? I can't, can I? Because if I've got one end that's going toward positive infinity and the other end going toward negative infinity, I will not have any absolute max or mins. So that tells me there are no absolute extrema. Okay, but I still need to figure out if I have any local maxes or mins. And to find those, I've got to find what? Say it again? The derivative. Okay, tell me what f prime of x is going to be. 3x squared. Okay, we saw this guy earlier, didn't we? This was the first one that all we did was take the derivative of it and identify what those critical values were. So let's just go ahead and pull that information we already got off of the first page. And that means that there were critical values. Where were they? Okay, positive 3 and negative 3. So I'm ready to do a sign analysis here. But this time, I have 2 points that I'm interested in. So I'm going to have to find out what's going on the left side and the right side of each of these. And since our factored form of this derivative was 3 times x plus 3 times x minus 3, you may find using the factored form for your derivative actually makes it faster, a little easier to figure out what kind of sign you're going to have when you come up with those test values. So we need to pick some numbers that will be in these 3 regions we can use as test points. What would be something smaller than negative 3? Negative what? All right, let's try a negative 4. What's probably the easiest number to pick between negative 3 and positive 3? 0. And then let's pick something larger than positive 3. Positive 4, why not? Okay, so those are going to be the values that we will test. Now, if I were to plug in a negative 4 to this derivative, a positive 3, that's just a positive number. And if I multiply a positive times anything, it never changes the sign, correct? So here's what I need to figure out. If I put negative 4 in this first parentheses, what's negative 4 plus 3? That would be a negative times, what's a negative 4 minus 3? That's also a negative number, isn't it? So what would a negative times a negative give me? A positive. Now, I realize I'm not coming up with a number. Do I need the number? No, any number that's to the left of negative 3, if I plug it in, it's going to give me back something that's positive. Is that making sense? Okay, I just want to make sure that makes sense because that's the fastest way. I mean, if you want to work it out and put it in your calculator and see what the number is, that's fine. I just really need to know if it's a positive number or a negative number. Now, if we look at 0, that's easier to figure out. Again, positive 3 is a positive number. It never changes the sign of anything to multiply by a positive. If I put 0 in the first parentheses, 0 plus 3 is a positive number. What's 0 minus 3? A negative. What's a positive times a negative? Aha. All of the values between negative 3 and positive 3, if I plug those in, it's going to give me back a negative number. Now, tell me what happens if you plug in positive 4. It's going to be positive because you would get a positive times a positive, because 4 minus 3 is a positive 1. And all positives multiplied together give me back a positive. So how many sign changes do you see here? Is there a sign change at -3? Yes, because to the left is positive, to the right is negative. Is there a sign change at +3? Yes. Now, here's what that tells me. If I go from positive to negative, that means this is a what? -3 is going to be, which one? A local max or a local min?
Local max.
That's a local max. Because it went from a increasing slope to a decreasing slope. Okay? What does that mean we have at +3? A local minimum, because we're going from a negative to a positive. So here are the different parts that we're supposed to identify. The intervals on which the function is increasing. If it's increasing, what am I looking for on this sign analysis? What would it indicate that it's increasing? Positives. Tell me the intervals where I have positive signs there. It increases from to which one? Do y'all agree with what Ashley just said? -infinity to -3. She is exactly right. Now, I'm going to close it off at -3. And since the actual slope is 0 at -3, and I know that's a turning point, you can decide if you want to close it with a parentheses or with a bracket. Either way is fine. Do I have another interval that is increasing? Yes, it also increases from where to where? 3 to +infinity. Very good.
Do we not put the U?
You can if you want, or you can just put the word and. But yes, you do need to identify both pieces. Okay? So it requires both pieces. Now, the interval that is decreasing occurs from where to where?
-3 to 3.
Excellent. -3 to +3. And that means we have a local max at -3, comma, now how am I going to find the y value where that occurs? I have to plug in -3 where? Good, in the original function. I want you to do that and see what you come up with for the y value. And then you're going to identify what the local minimum is as well. All right, so tell me, when you plugged -3 into the original function, the x cubed minus 27x plus 12, what did you get back for the y value? When x is -3, y was?
66.
That is correct, 66. We have a local maximum at -3, 66. Where is the local minimum? Did you get a positive number or a negative number? How about a -42? All right, and we've got one more that we're going to go through and actually take all these pieces where we find the different parts, and then we're going to put the graph of it together. So tell me, I'm going to have you guys tell me step by step, what's going to be the first thing you want to do?
Identify the way that the graph's going to work.
So our end behavior, good Ashley. So on this one, we could say this is our pre-calculus. So talk to me about what you think this thing is going to do on the ends. What would be my end behavior? Is it even or odd for an exponent? Odd. And is the coefficient positive or negative? All right, so it's positive and odd, which means the ends are going to do what? What does it do on the left side, up or down? Down on the left and up on the right. Very good. Okay, so we've got the end behavior there. Oh, now look at this one. is it easy to see where this thing's going to cross the x-axis? Or tell me what the y-intercept is. If I plug in 0 for x, what do I get back for y? Ah, guess what? It's going to cross through the origin, isn't it? Okay. Is there anything else that I see that might help me? Well, then let's move on to the other information we're going to need. So we've got the end behavior. We know it's going to cross through the origin. What else do we need? Start with the derivative. Good job. Okay, tell me what the derivative will be. Well, instead of 6x cubed, it'll be 6x squared. That's okay. Plus, minus 12. Good. Okay. And we're supposed to do what with this derivative? Set it equal to 0. Now, what do you notice we should probably do on the right? Yes, we've got a common factor, don't we? Pull out which number? 6. And what will that leave me in parentheses? X squared. Oh, come on. What comes next? Plus x minus 2. Okay, will the x squared plus x minus 2 factor? It does. Into what? What can I multiply together to get negative 2, add to get positive 1? How about a positive 2 and a negative 1? Won't that work? If we use FOIL to double check that, we do have it factored correctly. So here's what that tells me. I've got critical values or partition points that occur where? When x equals negative 2, positive 1. And am I ready to do my sign analysis? I think so. So negative 2, positive 1. Now what? Good. What would be a number to the left of negative 2? Negative 3. We can use that as a test point. What would you pick in between? 0. And then something to the right of 1? Maybe 2. All right. And I'm going to plug those numbers into what? The derivative. And if I use the factored form of the derivative, it makes it even easier to see the sign that comes back out. Okay. So if I plug in negative 3, what's that going to be in that? Because notice I've got a positive number factored out. Now, if I ever have a negative number that gets factored out, I have to use it when I'm figuring out what sign do I get back. But as long as it's a positive number, it's not going to change a sign if I multiply through. So if I put negative 3 in the first parentheses, what comes back out of that? A positive or a negative? Negative. And then if I put a negative 3 in the second parentheses, that's also negative. And a negative times a negative is a positive. So these must be positive. All right, what happens if you put 0 in? Negative. Because 0 plus 2 is a positive times 0 minus 1 is a negative, and a positive times a negative is a negative. And then what happens if you're putting in positive 2? Because it's a positive times a positive. So far, so good? Thumbs up? All right. What does that tell me? Because remember, I've got different parts I have to identify here. And one of them is I'm looking to see if I have any local extrema. Do I have one at negative 2? Is negative 2 a local max, a local min, or neither? Okay, and Julio, you say it's a local max because? Very good. We have a change from positive slopes to negative slopes. So that tells us this is a local max. And that means that 1, an x value of 1, is a local min. Very good. All right, so let's see if we can answer the questions and then we'll sketch the graph. So for A, give me the interval or intervals where the function is increasing.
Negative infinity.
Okay, so it increases from negative infinity to what? Negative 2. And then the second interval starts where? At 1. Yes, from positive 1 to positive infinity. Very good. Those are our two intervals that are increasing. And the interval that's decreasing is between negative 2 and 1. Excellent. All right. And in order to sketch the graph, what else do I have to find?
The Y-intercept. Oh, we already did that.
I need to know the point that's the local max and local min. I know the x value, I haven't yet found the y value. So the local max occurs when x is negative 2. Now you've got to find the y value. I want you guys to see if you can come up with that. And then you'll get the y value that goes when x is 1. Let's see if you can do that correctly. So what did you come up with for the y value when x was negative 2? Was it positive or negative? Are we having trouble coming up with the y values, or are we doing okay? You guys are making me nervous.
Is it negative 4?
That's not what
I got 20.
20 is what I'm looking for. Now remember, we're plugging this negative 2 into the original function. So that would mean that f of negative 2 was 2 times, you got to cube negative 2, plus 3 times negative 2 is going to get squared, minus 12 times negative 2. And so when you cubed the negative 2, that was negative 8, right? And negative 8 times 2 was a negative 16. When you multiplied negative 2 squared, gave you a positive 4 times 3 is positive 12. And a negative 12 times a negative 2 is a positive 24. All right, and so 36 minus 16 is how you get a positive 20. So make sure we're okay in cleaning up. When you put in 1 as your x value, what do you get back as your y value? Negative 7. Excellent. Okay, so I think we've got all the pieces we need to get this thing graphed. Let me see if I can sketch a graph for you here. So we're going to put a grid on here. You get to choose what kind of scale you want to use to mark it off. I definitely think I need to count by ones on the x-axis. You need to make sure you label. So 1, 2, 3. And then for my y value, since I'm going up to a maximum of 20 and down to a minimum of negative 7, I might count by 5s. Okay. And let's see if we can get these points on here. So what I do know is this thing for sure crosses through the origin. So that's a point that I had found in my pre-calculus. I also know that I've got this local max at negative 2, 20. Oops, that's a little sloppy. And I've got a local min at 1, negative 7, which would be about there. And my end behavior was down on the left, up on the right. So here's what I know. This is going to come down here. And then we're going to cross through the origin and come down here and then go back up that way. And that would be a sketch of our graph.